University of Göttingen, and they will be talking to us about algebraic units pretending to be squares.
Okay, hi everybody. I'm gonna try not to use too much complicated number theory, and let's see, where's the screen share on this thing? Last week's talk really reminded me that it's easy to lose people, so I'm hoping not to do that this time. Really let me know if I do. Okay, can you see the screen share?
Yes.
Yes.
Yeah.
Yes. Okay. So I'm going to start with, what is a number field? Because I know we haven't always dealt with them here.
Same turtle or different turtle?
Same turtle's being brought back to its
So the definition of a number field here is going to be, you take the rational numbers, we're going to call them Q, and you attach to them something else. But this something else is going to be any solution to a polynomial that has integer coefficients. So, you could take like x cubed plus 1 or whatever, and you take the solutions to this, the roots of it, and you attach those numbers. So you can use them, you can add and multiply them with the numbers you've already got, and you get a new number field. You get what the simple ones are if you like attach the square root of 5 or something. Right now you can use those too. What are the limitations of what you can do with this? That's what we usually work with in number theory. So in these fields, we have the algebraic integers, which are those which are roots of some polynomial that's monic. So where the first coefficient in front of the big power here is 1. These play the same role that the integers play when you're working with rational numbers. So if you're willing to move to ring ideals, you can take factorization involving them and that kind of thing. What do I have here? The problem with using these is that when you got a number in the integers, you got just something like 2. And that's the only thing you have to think about. A number is just one value. But when we move up into number fields and we're attaching all of these other pieces that are not rational numbers, first off, you have to consider that when you factor, you don't just factor the number, you factor in terms of the entire ideal based on it. So you can end up with lots of values that act like 2 enough that they end up in the same ideal. And we have to treat them for purposes of factoring as if they were part of the same thing, because we don't have unique factorization. Once you get to ideals, you're fine, but actually the numbers don't uniquely factorize anymore reliably. And what's worse than that is that you have embeddings. When you define in terms of the roots of this polynomial, you could have picked those roots in a different order and still gotten the same structure. So that's considered a different way of taking that structure and embedding it into the real or the complex numbers. Because of this, a number like 1 plus root 5 over 2 doesn't just stand by itself. It also has any conjugates that it has in the field, which are the other embeddings. And anytime you consider it, you have to consider these together. Now, this is a case where one of those embeddings is greater than 0 and another is less than 0. So with even with real numbers, you can end up with different embeddings having different signs. And when it gets to complex, it's even worse because you can have some embeddings that are real and some are complex, and it's just all over the place.
Okay, Kim, I have a question already.
Yeah.
So I'm not a number theorist, so I sort of remember that, like in your Q adjoin root 5, that one I remember I could think of any element as like a rational number plus a rational number times root 5, where it's sort of like linear in that way.
Yeah.
If I'd like write down all of the different roots, is it always a linear, like, are those roots always a basis over Q for the elements?
Okay, so
Basically what I want to know is that how I should think about a single number in your field, is sort of like those kinds of things?
kind of, yeah, but the great thing with root of 5 was that if you just square it, you're back in the rationals. Generically, if you have something like this, then the elements are going to be like this, but it goes only up to a finite power. Like eventually you're going to get back in the rationals and be fine again, because you're only attaching algebraic numbers here, which means they're the solution to something. Eventually you got to get to some power where it comes back out. But it's going to sum over the various ones that are available. So if you had something that was like a cube root, then you get first and second powers of it in these sums. And then these coefficients are all coming from Q.
Great, thank you. I always remember that I misremembered exactly how to think about the elements, and that I always got confused, so thanks.
One of the simpler approaches to that is that if you need an example number field for just doing something really generic, always go to the cyclotomic, which is just you take the roots of 1. So you've got in the complex plane, like just a circle. And each one of these, if you take it to some power, you're going to get back to 1. This is a very handy number field to choose because depending on how many of these you position around the circle, you can use this to encompass any abelian number field. Now, that's the Kronecker-Weber theorem. So once you have these in your imagination, anytime somebody says, have an abelian number field, you know what you're looking at. You're looking at a circle with partitions with like copies of Q going off in directions. And this puts a picture on it.
Great, thanks.
And everything I'm trying to do today is entirely in abelian number fields, so that'll work. Okay, unit, I would go back to the numbers in here. We had the idea of different embeddings. And if you're looking at these cyclotomic ones, then the embeddings are literally like you're spinning it around the circle. And each of these points here, like there'd be one embedding that takes each to twice as big as it. So that one would go there, but this one would go over here. And it just kind of stretches it. So you have, for every single number you might be considering in this field, whatever the dimension is of the field, you've got that many different embeddings. And the question that was coming up in a research context I was working on was, when are all of those embeddings for a real number positive? Like, you got real number line. This is back outside the complex plane, we're just an R. You've got some number out here. It's you know, a unit, so it's an algebraic integer, so it's its inverse. It acts like 1. These are the ones where when you factor all your ideals, it's just up to some unit. We don't care what unit. Well, sometimes we care about the units. So you've got this number in R, and then it's got a bunch of other embeddings, different places it can show up depending on how you like rotate these values around. But what has to be true for all of those to be greater than 0? And this is why I say these things look like squares. Because if you take any number in R, like back to algebra 1, that number squared has to be at least 0. So we already know that anytime you take a unit, if you square it, you're immediately going to get something that that's greater than 0. But is that the only way it can happen? And this question's been investigated for a very long time. The first result that we got on it was actually by Weber. So we have results going all the way back into like 19th century. And the fields that Weber was considering was take the rationals and you extend it by a root of 1 that is to a degree some power of 2. Then you look at just the real part. And he was able to prove that the only ones you have here are the squares that do this. Every unit there that's not a square has at least some negative embedding. So there were attempts to extend his proof type to other cyclotomic fields, and those methods completely didn't work. One of my favorite publications is actually of someone trying this, and it's my favorite because it didn't work. And they literally published an article of, here's what happens when you tried this method, it doesn't work. I wish we could get away with that now. It would save people the time and effort of doing it 3 times. So this was pretty much the state of the art until a guy named Davis at Caltech, his thesis in, I think it was 1968 or so, he came up with a conjecture, which was that if you take the ones where it's just a prime and specific kind of prime, Sophie Germain prime, he conjectured that here we do not have this unit. That conjecture is still open. It has not been fully resolved yet. But it seems like not having these should be the default condition, right? It should be weird to have them. So we need proof that they ever happen. And that, in fact, we have very easily, because if instead of taking a prime, if I take something here where this number is not a prime, it's like some whole bunch of things put together. Who cares what? But it's not a prime. Then automatically there exists one of these units. I can show it to you. It looks like this. Take your root of unity and subtract its conjugate. And then take the norm of this from that field, call it K, down to its real part. So you've taken a purely imaginary number here and multiplied it by its conjugate. That's going to be negative. Put a minus sign in front of it. You have a positive number. And the reason why it's positive did not depend on which power of zeta was in there. No matter, you could replace this with zeta sub m to the a, any a. You're still going to have this times its conjugate is real and greater than 0. So these exist in the composite cyclotomic fields. The real surprise that Davis was able to show was that in very, very few of the prime cyclotomic fields, these still exist.
Oh, we had a question, which I was thinking I should ask anyways. Norm. So.
Oh, sorry. Norm. Yes.
I mean, they're complex numbers, right? So it's just the usual norm of a complex number, square root of the real coefficient plus the imaginary coefficient.
Okay, if you're working with just a quadratic, you only have these 2 embeddings. If you're working with something more complicated, like you start with Q here, and then you've got, well, here, for instance, we'd have our real part, and then our imaginary part here. Yes, here you're just going to take, it's of degree 2, you're just going to take the number times its conjugate, and that's going to be your norm. But in every case with number fields, when you're taking a partial norm or a total norm, what you're doing is taking all the embeddings that are different up above, but not different down below, like the ones that change in this part that you're wanting to do the norm over, and just multiply them all together so that you get something that lives down below. Because if you did any of the transformations that would turn these into each other, it would just move terms in the product and not actually change your number.
Great.
Does that somewhat work?
So the goal is just to get something in the subfield, and there's this trick where you can make something really symmetric.
Yes,
to accomplish
exactly.
that, but you basically the goal is
equations.
just to get something symmetric that reduces to the lower.
Yeah, it's
okay.
totally based on symmetric equations. When this started being done a lot in the what century? 19th century, they would actually use all the symmetric equations at first because they weren't sure which ones would work well. And then it started being, okay, we've got these fundamental set of symmetric equations out of which all symmetric equations can be built. Let's see what those do. And slowly they realized that you only have to look at the 2 extreme ones, where you're either multiplying everything together or you're adding everything together. So those became the norm and the trace. And at this point, those are the only ones we really use anymore.
Okay. And then in the example you were giving, it was, zeta minus its conjugate, which, as you pointed out, is a completely imaginary number. And so that in that situation, norm it's always degree 2 over the reals. Oh, but maybe not the rationals. So it may not be the
over reals, but not rationals. Yes,
that's where I got
maximum
confused.
real
Okay.
subfield. This is a type of field called a CM field because they were developed based on complex multiplication properties. And you've got all this real structure built up, and then you just split it in half in the complex plane at the top. And
Okay.
all of the cyclotomic number fields follow that particular structure.
Great. That helped my intuition. I got a couple of questions. Does that help everyone else's intuition? Yeah, great. Thank you.
Okay, cool. Because, yeah, I thought I'd be able to follow the chat at the same time, but I'm finding my eyes are in too many places. So, where was I? Okay, yeah, we have an example in the composite cyclotomic, but Davis was able to construct an example in a prime cyclotomic field. Hey, cat! Hey, cats. And the way that he constructed the example is almost as strange as the fact that it exists. The example is a little bit complicated. I mean, I can write it out, but you have to take the cyclotomic units, which form like a really nice layer of units inside the real field there, and then multiply a bunch of them together. You don't just take one, you have to make like this weird product inside it. But what he did to find these is he turned the problem of the sign of a unit and its embeddings into a linear algebra problem. I see that grin. Yes, everything is linear algebra. Even number theory. So if you have a unit and you want to make all of its various embeddings, then each one of these is going to have some sort of an associated sign. And you can create a cute function over these if you have like, you have the homomorphisms that create them like this, so that you have one homomorphism from the Galois group associated with every one of the embeddings produced. Then you can make a cute little function over these, which is called the signature of the unit. Where you just take the sum over all of the possible ones that you could apply to it. Oh, I'm not going to use a sigma for that. That's annoying. Actually, the sign of that applied to it. And then you tack the element of the Galois group on the end. And you get an element of a group ring over the Galois group. And this gives you a huge amount of structure. But what you do with it boils down to these numbers plus and minus signs right here. Because you're going to turn those into just ones and zeros. And what you do, you take a fundamental system of units, because the unit group has basis. And luckily with cyclotomic ones, we tend to know what's going on. But it's finite. It's got a finite basis. And then you take all of the embeddings of each one of these, make a matrix. It's just got these ones and zeros in it from whether it was positive or negative. And you can ask a good old-fashioned linear algebra question. What's the rank of the matrix? If you have everything's independent, you've got full rank matrix, then you don't have any of these imposter units. The only times that it looks like a square are when it's a square. These are actually equivalent conditions. It's not always easy to construct this thing, and Davis ended up having to do a lot of manipulations on it to turn it into something that could be constructed on a 1970s computer and run for 2 weeks. But that's how he was able to verify for primes up to 1,000 which ones actually do and don't have these units. Turns out, got a few of them. You got 29, 113, 163. And
Everyone's favorite sequence.
like a couple dozen more. Much to my surprise, until last year, it was not actually on the database of integer sequences. It is now, but it was oddly overlooked. Let's see. Double check my plan here.
Does anyone here recognize this sequence? I don't.
So what can you do with one of these? 163. Well, half of why it shows up weird places, I keep saying it weird places, and this is why it's on my mind and why I keep doing that. So what can you do with one of these units that you can't do without it? I don't know if I can get to any of the definitions behind it, but if you know any class field theory, whether these exist, at least in cyclotomic fields, tells you exactly whether the class number is even. Yes, I see somebody in the chat. No, we don't have a full list of number fields with class field number 1 for the positive side of things. But I can tell you that cyclotomic with prime 163 is not one of them. And this is why I can tell you that, because there's a equivalence proven by Steffenhagen that if you have a totally positive, real, non-square unit, class number is even. So I don't know what it is, but I know it's even. At least getting to say something about the class number is usually a pretty big accomplishment with these things. The other thing that we can do with them is build a type of extension that's otherwise pretty tricky. So suppose I had a unit, I'll call him pi. Please don't make me call it p. And it's one of these totally positive real, these units. What if I took the square root of negative that and extended, hey, no, I can't reach over there. Okay, take a number field that contains pi and extend it by this thing where this is real. You're going to get a number field that is imaginary and contains more units than the original. Same order of unit group, but there are units in there that are not in the original one. Some of them will be purely imaginary, and the extension is not ramified. That's the only way you can build these extensions. Otherwise, you're going to get some kind of a prime that ramifies. which I didn't talk about ramifying primes, but it's a property that we usually either try to avoid or try to limit because it complicates the problems a lot. The more of your primes do that, the more it hurts. Oh no, I don't want anybody to be out of their depth. Where did I lose you? Yes, infinitely many units is a headache, but it's not too bad because you still have a decomposition. Your unit group is always going to have a form where you've got torsion part, and then you've got some copies of infinite that look like the integers. So even if you've got infinitely many units, you're still okay. You know, you've got some kind of a basis for this. You might not know what it is, but it exists. And this part is finite. So having infinitely many units hurts only a little bit. Even if you've only got a quadratic field, go back to our friend. This is always our friend. We like this field. He has infinitely many units, but we know what they look like. They're just powers of this guy. Wait a minute. That's the algebraic integers. These are the units. Just these two powers. So if we have the ones that look like squares but they aren't, then we can make these unramified extensions, which show up in some surprising places. I actually ran into them trying to work on Lucas numbers, which seem completely unrelated. But the weirdest thing to me is that if you take this composite cyclotomic field, where you've got stuff associated to one prime going one way, stuff associated to another prime going another, and you're just kind of putting these together. So I'm just putting the real parts together here. It's actually got a little bit there. Now I'm going to put just the two parts. Now everything here is a power 2. We know there is one here. We know there might be here in the rare cases that Davis found. Usually not. There's a theorem by Garbonati that says there's definitely not one here. But everywhere else in this, we have a few hints where it can be and where it can't, but it's not completely solved. Even in the quadratic case where you've just got an extension of degree 2, it's not completely solved. And there, it's an equivalent problem to whether the norm of the one fundamental unit you might have is plus or minus 1. This looks like the simplest question that you could possibly ask about a quadratic number field. Yes, it does look like a baseball diamond. This is my baseball diamond diagram. I wish I could extend the analogy further, but I never played baseball. swear my notes were organized when I started. What have I not done? Almost anything on here. Oh dear. There's one case where that diagram, there it is. There it's not. Yeah. Simplifies a lot, which is, what if this part disappears? What if you have no two part? That would make it really simple, right? Then whatever's happening here would just trickle down and you wouldn't get any new behaviors in the middle. That happens anytime you have like the prime is congruent to 3 mod 4. Then the two part disappears completely. So when you see number theory proofs, they very often start with case P is congruent to 3 mod 4. And this is why. We don't like dealing with 2. 2 is the oddest prime. So first thing we do is get rid of it. So we'll always work with primes congruent to 3 first as best we can, and then look at ones involving 1. And if you look just at those congruent to 3, where did I put that result? Oh no, where'd it go? Huh. Yeah, on the quadratic side, down near the bottom here, if you have something like this, and then some prime divides M, where the prime is congruent to 3 mod 4, then you've lost one of those sides of the diamond, and suddenly we know that there exists one of these totally positive not square units, because it's going to have some fundamental unit, and the norm of that fundamental unit is minus 1. I mean, it's going to be 1. Excuse me.
I think she might have eaten something.
The problem with the quadratics is that, as I said, we don't know everything there. What if I have this and all of the primes dividing it are congruent to 1 mod 4? Could happen. You could just pick those. Well, if you only have 2 of them, there's a pretty classical result on it, which says that if the Legendre symbol of these is equal to -1, then we get that the totally positive, no, we don't get the totally positive. What? Hold on. Yeah, then we get that all of the totally positive are square in that field, which means that the fundamental unit has norm -1. When you go above the quadratic and you get into the much larger fields, it's no longer a fundamental unit that has a norm plus or -1. You have a whole set of fundamental units, and whether any of them has a norm -1 is almost equivalent to whether these totally positive real non-square units exist. Almost. Usually, if there exists some unit with norm -1, these things don't exist. The exception is these units found by Davis. They're the only case I've come across in the literature where you do have units with norm -1, but you've still got the weird units. And I have no idea why this one situation falls into that gap. I mean, you have lists and lists of weird rules for these things. Like you have no unit with norm -1 if there's some prime congruent to 3 mod 4 dividing the discriminant of the 2-part, or if there is 3 dividing the conductor of the field, or is really weird criteria for these where it goes together in terms of the weird units and the existence of units with norm -1. But specifically, the ones in the prime cyclotonic field, they're appearing in the odd part, only on these few primes, the symmetry between these two properties is broken. So they're even weirder than they look.
This reminds me a little of learning about Stillo's theorems in grad school, where there's just like 12 things you can try, and you hope at least one of them works for you. And if it doesn't, then you try something else, and then you bootstrap your way up. Is it?
Well, you know, Stillo theorem is why I keep saying two parts. Because in fact, that is why you can split off part of the number field and just say, well, everything here is the degrees of power of 2. The only thing going on here is 2. If it weren't for the Stillo theorems, you wouldn't be able to take that part off to the side. And it only works on abelian number fields, which thankfully is where you usually work. So, okay, I'm looking at the time, and it looks like I have rambled for around 45. I'm looking if there's anything I've completely overlooked here.
So, well, in terms of your ideas, I don't know. In terms of questions, I think we've said most of them out loud, although I don't remember what the genre symbol is. But I was wondering, sort of what I'm getting is the big picture is there are all these different techniques, right? And I don't know, I'm a geometer by training, I guess. So is there any sense in which there's like, you know, some geometric interpretation of each of these strategies, or are they all completely random?
Well,
like where are these ideas coming from to do these different strategies?
Very much of it comes down to how we break up problems, and I am dismayed that I was not more organized to be able to reveal this more clearly, but you have breaking apart the number field into the 2-part and the not 2 parts. And this comes from that the sign of something, you know, plus or minus 1 is a property of order 2. So you want to get the 2's out of the way because you're trying to do something involving 2. And then when you look at cyclotomic fields and you're trying to split out the 2-part, you end up seeing that it only comes up when you have the prime congruent to 1 mod 4. So you start with the ones that are congruent to 3, you start looking there. Separately, somebody will start looking, well, maybe it's easier with the 2, so let's look just in the 2-part. Look just at fields that are degree 2 to some power and see if maybe, what if the discriminant only had 1 prime? What happens then? Okay, what if the discriminant only had primes that were 3 mod 4. Maybe we don't want 2s there. And that's how we sort of split everything up and try to come at it one piece at a time. Because yes, unfortunately, number theory proofs tend to devolve into an absolute mass of cases. But there's a structure. There's a way these cases happen, and it has to do with the way the number fields themselves can be broken apart. So the first part of it is just in terms of primes, like can we do individual primes one at a time and then recombine it into a composite structure? But then you look at what kinds of primes are easier. And that's why Davis looked at across the whole slew of primes. Now, brute force with a computer, once he turned it into linear algebra, where does this happen? And then when he formed a conjecture from it, it was maybe not the most general conjecture that you could fit to this data. It was on Sophie Germain primes. And these are ones where the maximum real field inside the cyclotomic field is of prime degree. So you've only got one cyclic part in it by Stillo theorems. Just one. The idea was maybe this will be simpler. So yeah, that's how we break it apart. At least for me, reading number theory papers gets immensely easier if you know to look for that structure.
Cool. Looks like we have.
Yeah, go ahead.
No, I just looks like we have time for questions. If anyone else wanted to unmute and ask a question.
Yes, please. Now I'm better at rambling than I am at going off notes.
One thing that I really would almost want to see, if it's possible, is could you give us some more concrete examples of what some of these actually are? Like, just like I'd almost want to be able to say, like, it feels like there should be like something I should be able to just write down that's not a square, that like I could write down that like a pre-calc student recognizes a number.
I'm not sure that this qualifies as recognizable as a number, but this is the simplest surprising one that I know. So if I define the cyclotomic units as C zeta bar minus bar for every I up to size that we're using for our prime selected to be 29. And then we multiply these together, particular ones of them. That's why I didn't write it out earlier. I'm afraid this thing's a bit of a beast. That's literally the simplest example I know. And it is, in fact, the only one I've seen calculated out explicitly. That's the one that Davis found for the cyclotomic field with p equal 29.
Is there some rhyme or reason to the choice of subscripts there?
You have to use those specific ones-ish. The thing is, if you take this number field and you perform an idempotent decomposition on it, you can extract a simpler version of this unit in a degree 7 subfield. And that one is considerably shorter and can be written in terms of the group action. But I don't have it written down right now. It's in a notebook somewhere.
So is it relevant that those subscripts are all prime powers? Is that?
Not really.
That seems such a nice conjecture.
Yeah, it really is. And it's cool that you noticed that. I actually never noticed that about them. But as far as I know, that's unrelated to what they do.
Can I ask another one? Is this notion related to any other notion of pseudo squares that comes up in number theory?
If it is, I'd love to hear about it.
One of the common ones is composite numbers with Legendre symbol 1 are pseudo squares. I don't know.
I haven't seen any connection.
Yeah.
The only place that the Legendre symbol has come up in this is basically Legendre symbol -1, representing a lack of interference, basically, between two primes when dealing with the quadratics. And
Right.
otherwise, I haven't seen any connection there.
Well, number theory always felt like another path I never followed. I'm an algebraic geometer by training. I always loved it. And then, my colleagues would start talking about the bounding, some analytic continuation, something, which just never spoke to me. And so it was really interesting to sort of see something that felt more like a group and ring theoretic number theory, that was really fun. I really appreciate that offering.
See, I'm an algebraic number theorist, and when my colleagues start talking about stacks and sheaves is when I tune out and break down.
Ramified covers. There we go. We're all talking about the same thing.
That's it. Yeah, I can barely get that.
Great. Well, just to make sure we get this in before we run out of time, this is our weekly announcement. I don't think Nanad is here, but our talk next week is about rich mathematical tasks in mathematics education. And so I'll leave that up. And this is a colleague of Kate's. And so I'm looking forward to it. And yeah, so could everyone please join me in thanking Kim for this interesting talk?
Thank you.
If anybody wants the more technical view, I'll put a few references over on Twitter.
That would be great.